So my name is Marcin Matuszak. I came from Poland, and I'm working as a data engineer for Ryanair. I think everyone knows the company, so I won't introduce much. And if somebody wants to know what we are doing or what I'm doing at Ryanair, I encourage you to come and speak to me after the conference. I am data engineer at Ryanair, so I'm basically doing the same thing every data engineer is doing, so I'm waiting for Spark job to fail. So today, plan is to talk about the immutability. Then we will have some short introduction, a little story, because every presentation needs to have a story. We will talk about optics and zippers. And the first point, immutability changes everything, is first of all, really nice post, a paper and a presentation by a guy named Pat Holland, I think. And I really encourage you to read this paper. And why I use this title? Because I think that everyone who is at least my age used to work with the languages which doesn't support immutability by design. So you work with mutable things like, I don't know, hibernate entities, with Java collection, etc. And at the moment when functional programming start to gather the attention, immutability became a very important thing, and it required to change our thinking and the way we are approaching to algorithm, the way we design our data structures, and the way we are programming. So that's I think that's why I use this title. There are two terms, one which is immutability and another which is persistence. And persistent data structure is a data structure which supports multiple versions. So this means that once you update or change the structure in some way, then somewhere in the memory, you will have a previous version which you can access at any time, because you have a reference to this previous version and you can do something with this. Immutable data structure are the data structures which doesn't change. So they usually even don't care about supporting previous version. And usually these terms are used interchangeably, and so I will do. And why I'm talking about this? Because parallelly functional data structures are always persistent. So they always leave a trait or leave a path behind with the previous versions. Okay, so why immutability is important? Because it guarantees that objects will remain unchanged during its lifetime. So once you create an object, it won't be changed by any other, I don't know, method, function, thread, or so on. So once you create something, it will be unchanged. You can try to update, for example, this, but then you will create another object. This leads to thread safe. So you can share safely the object between threads, and nothing won't happen. In mutable world, once you try to share something mutable between different threads, then you have to worry about the synchronization, worry about putting locks, etc. All next point objects are always in consistent state. So this means that there isn't a gap between creating an object and fully initialized object. So for example, if you have in your previous life, once you were working in Java, the typical pattern was you were creating an object with empty constructor, then you had a bunch of setters, and after setting the last one, the object was like ready to use. And it could lead to problems that someone could use this object in a time when, during the time when the object wasn't fully initialized. Also, for example, the typical pattern I used to see in Java world, it was like throwing in exceptions inside the constructors. So it also could lead to inconsistent objects. And immutable objects are good for caching, pooling. They have. I don't want to go to the philosophical part like Rich-Hickey, where you have state and identity. Basically, in immutable object, you don't have a problem, for example, the one you had with Hibernate, when you want to define the identity or equals and hash code. You don't have this problem because nothing can change. And as it shows up that immutability is a consequence of referential transparency. So once you are doing partly functional programming, then immutability is like out of the box. Okay, but the real world isn't mutable. It's not like you have a, I don't know, bottle of whiskey. You open the bottle, and you have suddenly copies of bottles, one which is open, one which is closed. So in real world, the immutability is more like a philosophical concept. Even people who are working as accountants and they are keeping the ledge, they are not creating immutable object, but they are working in something like append log. Someone may say that we are giving up an efficiency when we are working with immutability. That's partly true, but not always. And we are giving up a convenience, and that's true. That's why we need some tools to work with immutability. What I mean by efficiency? Wrong choices. We are choosing wrong algorithm to wrong in wrong places. Like, for example, we are choosing, I don't know, appending to the end of the list or updating the elements inside the list. So this is a choice of a wrong algorithm. There are sloppy implementations. For example, you can implement reverse method in list in linear time, or you can implement reverse in squared time. And also defensive copying. By this I mean the deep copy, for example, the one you know from the Java world, when you have to copy all the hierarchy tree of objects to make sure that the object is immutable. And convenience. Imagine we have some case classes like this, and once we create an instance of the object, so D is taking C, the C is taking B is taking 2 A's. And if we want to update the most nested A inside this structure, then we need to write code like this. Once it is really, it's not maybe really difficult to write, but it's pain to write code like this. And also it's very easy to make mistakes like this one, that you are trying to, you are updating one field, but reading from a different one. So this can lead to bugs, and which are usually really hard to find. And also, if someone is coming to, let's say, to Scala world and wants to start learning, when he sees something like this, he's lost. He won't come to Scala. He won't do anything in this language. Another example is a tree. It's a really simple tree, like you have a sealed trait, which defines the tree. You have a leaf and a branch, which takes a left value and a right. So nothing fancy. And once we create an instance of the tree, and we would like to update something, we have to deconstruct the whole tree. So once it's error pronoun. Second thing, it's not efficient because after the updating the field we would like to update, we have to reconstruct back the whole tree. And the line we are interested in is this one. And can you, looking at this code, say which branch I'm updating? You have to really spend a few seconds, squeeze your eyes to know what we are updating. Okay, and a short story. This is an Enigma. This is a machine used for ciphering messages, and maybe I should tell why I choose this example. Because this is a state machine which is immutable. And at the time when I was preparing this presentation, I was reading a book about the Enigma, and I was looking for some example, and it hit me at one point, so I decided to use this example. So it was designed or invented in 1918 by some German engineer, and it was later adopted in civil companies. And after that, when it showed up that it's really working, military started to interested in this machine. It was designed in 1918, as I said, and it was cracked when almost 16 years later, in 1932. So it took people 16 years to crack this machine. And the basic building block of this machine are rotors, which are, something like this. You have a rotating piece with numbers 1 to 26 or letters, depending on the design. They rotate in both directions, and they are built this way that they have input and output pins. So on one side you have a small notch, and on the other side there is like a spot, and they are connected, but they are not connected like A to A, but they are connected in different ways. For example, A can be connected to Z, B can connect it to W, and so on. So the whole power was hidden inside the rotors, which had these connections, and the connections were not revealed. Moreover, you could pick from one of 5 rotors, at least on 3 from 5 rotors. So each time you could have different combinations. And the wiring looks like this. You have input A. It goes through the first rotor. The first rotor connects A with some other letter. Then the middle rotor connects the second letter with some other letter. Next, third rotor connects this letter with something else. And you have a reflector, which is a half of a rotor, which transmits the electric signal back. And again, you go through the 3 rotors. Once you hit a letter on a keyboard, then first rotor rotates. The connections are changing, so the letter is now connecting the different letter. And once the first rotor is rotated 26 times, the second rotor rotates once. Once the second rotates 26 multiplied by 26 times, then the third one rotates once. So you see that it's quite complicated. To make it even more complicated, they added something like a plugboard, which allowed to swap letters. So once you hit T on the keyboard, the T was changed to K. And then it went through the 3 rotors, reflector go back and through the plugboard, and there is a lights which lead the letters. The second reason why I'm telling this is because the guys who cracked the machine were Polish mathematicians. So this is one thing which I wanted to go around the world and say. Another thing is that everyone who knows the Enigma machine, or at least knows a little bit about the machine, thinks that it was cracked by Alan Turing and his fellows from Bletchley Park. Actually, these Polish mathematicians, they open source their findings or their documents to English and to French military just before the war started. The second thing is that up to this time when they were when they cracked the machine, most of the ciphers were approached by people who were studying languages. So it was the first time in history where mathematicians began to work on ciphers. The second thing is because they were able to find patterns, and one of the guys who was called I think Różycki, he was studying group theory. So he was able to apply this group theory, and at the beginning of the previous century it was something new. He applied this group theory to crack the machine. Okay, so now go back to Scala and optics. What I want to do is to try to implement the Enigma machine using optics, and then try to replicate or recreate the first step of cracking the machine, or of the thinking process of the guys using the zippers. So optics are data structures which allow us to work on immutable data structures. And from history point of view, the first optic was a lens, but we will start with ISO. In here you have a hierarchy of optics, which is taken from Monocle. This is type level library for optics. And at the bottom you have an ISO. And if we go up in the hierarchy, then you will have some of the properties weaken. So for example, Prism allowed to have undefined state, and if you combine Prism and lens, then you can have an update which may fail. So ISO. This is a short for isomorphism, but if you go into lenses, it would be better if it would be called mirror, but we will stick with the ISO. So ISO is basically are two functions which are combined, not composed, but combined into one object. So first method, maybe the types. S, you can think as S as a type in domain. A is a type in codomain. So the get method is taking something from S and map this to A. Reverse get takes something from S and maps this to A. And this is lossless, which means there always will exist a path from S to A and from A to S. This is the basic property of isomorphism. You can think also, maybe this image will show you or clarify this, what I'm saying. So you have a domain and codomain, and you can go back and forward from one to another. Examples of ISOs are, for example, changing the Celsius degrees to Fahrenheit degrees. For every Celsius degree, there is a mathematical formula which will convert it to Fahrenheit. You can always change metrics, for example. You can always go from meters to centimeters and from centimeters to meters. These values are always defined. You can go between different types. For example, you can, for example, make an isomorphism between string and array of characters in both ways. So if we go back to our rotor, we can simplify it to something like a box with inputs and outputs and some connections which are inside. And as you can see, this is isomorphism, because we can find a mapping between left side and the right side. So we can write isomorphism between character and a character. For the moment, we don't care about the implementations, But to create the isomorphism, we have to provide get method and reverse get method. But now you may ask, what's the gain? At the moment, nothing. Okay, this is how you can use this. So you have a forward mapping and reverse mapping, which we basically don't care for the moment. And you can create the isomorphisms from these two functions. And once you have this one, you can call the isomorphisms to get A, you will get B, and reverse get for E, you will get D. Nothing fancy, but you will see the power of this in a moment. And one thing is you can compose isomorphism the same way you compose two functions. So having a function from A to G, G to H, is the same as having a function from F to H. So the same for the isomorphism. If we have a mapping between first rotor and the second rotor, or input of the first rotor and input of the second rotor and the output of the second rotor, it's the same as having the isomorphism between input of the first and output of the third. So again, we are defining the isomorphisms for left and right. We are skipping the implementation, and we can compose them. This is an example where I will provide some implementation. So you have a wiring 1, wiring 2, and wiring 3. So you can imagine that these are the wiring inside the rotors. So for wiring 1, you have A at the first position is mapped to E. The second position, which is B, is mapped to K. Third, which is C, is mapped to M, and so on. So the second rotor at the fifth position will have S. So this means that A is mapped to E, and E is mapped to S, and so on. We are creating some additional objects which will represent our setup. So the way we are setting up our rotors, or the way we are choosing them from our set. Here is some example of implementation. It's not safe, but for now it's enough. And we can create isomorphism for first rotor and the second rotor. And this way we can compose them together. And if we take our rotors and then we get the reverse, so we will get the same letter. Nothing fancy in here, but in the moment we will see the true power of lenses. Does it make any sense? Right? Huh? Second one, the prism. So if we go in our hierarchy to the left, my left, your right, we will end up with prism. And as I said, if we are going up, we are lowering our constraints. So in case of prism, we will have a possibility that when you are trying to get something from S, you can end up in undefined area. To make it more clear, we have domain, and inside the domain there is this pink-purple area. If you try to pick something from there, you see that there is no pink area in the codomain, so you will end up with undefined, in this case, none. To make it even more clear, once the Enigma message was encrypted, or the message was encrypted with the Enigma, then it was sent through the wire or through the radio. And it was possible that at some point someone would make a mistake, and for example, instead of letters, someone sent in with Morse code numbers. And in this case, as you remember, there was on the keyboard there was only 26 letters. There was no numbers, there were no punctuation, and so on. So from our business model, numbers are not allowed. So we can write Prism, which will take input, and in case of letter, we will return this letter wrapped in some. If it's not letter, then we will return none. So basically, again, we have two arguments to our constructor, to our apply method. One which is the function get option, and the second one is reverse get. And if you provide valid argument, then you get the valid output. If you provide invalid argument, then you get invalid output. And again, you may say why it's interesting. Because you can compose Prism, and you can compose this with isomorphism. And here, where it starts to be really useful. So first step, you are taking our validation of the input parameter. Then we are composing this with our isomorphism representing rotors. Then we are composing with reflector representing ISO representing reflector, which I didn't show, but this is the same as rotor, but half of it, and it connects wires back. And we are composing this with reverse isomorphism for rotors. So we have the full path from input to output. And this way, in here you have some cryptic methods to make it shorter, make it nicer. And once you provide a valid input, or you apply the Prism to valid input and call the get option, then you get some value. In other case, you get none. Lenses. Usually when someone is reading or hearing about the lenses or optics, the lenses are this data type which he come into. So in hierarchy, it's on the right side. So it's on the same level as lenses. And in this case, it's a little bit different because we are allowing to get from we are having a method which gets us from domain to codomain. There is no method which will allow us to go back from codomain to domain, and we have a method which allows us to set some value to make an update. And one very important thing which I didn't mention, but I will go back to this in a moment. So the lens, as you can see, they allow us to zoom into a data structure. So we can think as something which is of product type. So case classes, you can zoom into field of a case class, and from whole, you can select some part. Does it make sense? And to complicate our example, not to work on primitive types, we can introduce rotor, which will represent our rotor, and we can have current har. So this is the current setting. Each rotor can have the wiring. So this is how the wires are connected inside. And we have notch we can neglect for the moment. Yeah, we can neglect this. And we have Enigma machine, which consists of 3 different rotors. So now if you want to update the nested or to move the rotor one rotation forward, we can define rotor lens, which will allow us to zoom into the character inside the rotor. So the first argument of the constructor is C, which is get. The second one is update, and in this case we have to provide, we have to use the copy method. The second thing we have to provide is the way to focus from the Enigma machine, which has 3 rotors. So ideally, we would need to have 3 different lenses for each rotor. And again, we are taking the first rotor, and we are providing the the way of updating the structure. If you go to the documentation of Monocle, you will find that there is an easier way. You can generate this using macros, so you don't have to write this, but for the educational purpose, it's better to write this by hand. And if we have our lens which takes a rotor from Enigma machine, and then from this rotor it takes or make focus to the character, then we compose these two lenses, and we can have a lenses from rotor machine to our character. And if we make some instance of this Enigma machine, then we can apply this lens which we previously defined, and we can modify the car by one. So we will add one to car, and this will move our rotor one move forward. Okay, does it make sense? Or is it boring? No. Okay, so the second thing are the zippers. And again, I will make some, I will go back to our Enigma example. And the way the soldiers encrypted the message was they had this code book, which was a sheet of paper with date. Walzlage is a rotor, so they could pick 1 from 5. This third column is the setting, so it could be, in our case, the letters. And we can skip the rest. So for each day, they had this big sheet of paper, and for each day they were choosing the settings. They were setting this on the Enigma machine, and with these settings, they were encrypting the message, and the message was sent. And the person who received this message was also setting to the initial settings, was typing this message back, and he got the decrypted message back. So Army introduced another difficulty to this. They thought it's difficulty. They introduced something which will, one, make it more difficult to break, and second thing, it will work as a checksum or something like this. So they decided to pick 3 random letters, encrypt them with the initial setting, then again encrypt these 3 letters, or maybe they pick 3 random letters, they made 2 triples, they encrypt this 6 letters with the initial settings, and then they set these random letters to be the next initial settings. I don't know, am I clear enough? You will see example. But usually when it comes to randomness, there is a problem with people, and they overuse this technique. So I will show you what was the flaws and which leads to breaking the Enigma machine. So first, they decided to use AAA. So at the beginning of the message, there was 6 A's. The initial setting for today was RTD. So using this RTD, they encrypted the 6 A's. And using the AAA, they set up this to the initial setting, and they encrypted our message. So they end up with something like this. But the problem was that they used this AAA twice. In their opinion, it was for making the message more reliable, because once they get 6 A's, they were sure that they received a message which is not corrupted. But our mathematicians, they found something interesting. They found cycles inside this code. So the first row is the first 3 letters encrypted. The second row are the second 3 letters encrypted. And they discovered that when they compare first letter from first row and first letter from the second row, so the first letter, they will find some cycles. So they go from B to T, from first T to first Y, and so on, and they end up with B, so they found a cycle. Again, this is the second cycle, and this is the third cycle. And they go on to the second and fifth, third and sixth column, so this way they had all the cycles, and using the category or the group theory, they were able to write some equations and found some solutions. So we are going back to zippers. In the moment, I will show you how we can approach this problem with zippers. So in 1997, the guy called Erard Wiet, he's a French, he wrote a paper. He didn't discover this, but he was the first one who wrote this on paper. So he described that, basically, I can summarize this paper in one sentence, that updating the head of the list or the head of the tree is constant in time. And basically, this is the idea of this paper. And based on this, he proposed metastructures which we can build upon normal structures. So one way to describe the zippers is the functional cursor into data structures. But I want to think about this as a metastructure which allow us to update structures for free. So basically, we don't have one zipper for every structure. At least we don't have this in Scala. We have something in shapeless, but I don't know how it works and how this compares to Haskell. And in Haskell, you can have a generic zipper which will work on any structure. In normal Scala, you have to write your own zipper to each structure you want to work on. So basically, the zipper is something which contains left list, a focus, and a right list. And I will show you an example in a moment. What does it mean? So we can break our initial list on these three parts: lefts, focus, and right. Again, you can implement this in many ways. You can implement this using two lists, but I think using the focus, it's easier to understand. And you can define operations which are allow us to move left on our list, right. They allow us to modify, delete, and the final method is commit. There are much more methods, but these are the most popular. So as you can see, there is left and right, it returns option, which means that it's possible that when you try to move to one direction, there is nothing, then you will end up with none. Usually modifying doesn't behave this way, and delete, it's option because you can delete the focus in some implementations, and then you will end up with none. And all of these operations, apart from commit, because this one is using reverse, are constant in time. So it's not depends on the size of the list. It will be always constant in time. The only ON method is commit, because this depends on the reverse method. So again, we have these cycles which we defined earlier. We can write this as a triple. So we have 3 hars, first, second, third. We have our setting, which is the left triple, the right triple, and the cycle. And we can define this list like this. We can have a helper lens to zoom into our cycle field inside the settings and update this. And now we can start to work on our data structure. So in our first, inside the for comprehension, first we are modifying this and we are marking this as a first cycle. Then we are moving forward right. We are marking this as a first cycle. We are skipping next because next, as you can remember from here, the third element was different cycle and so on and so on and so on. When we go through our structure, at the end, we can commit this and get the original list. I know that this example is a little bit stretched to fit my presentation, but now I will show you maybe a simple example. We'll be using lists, numbers. So if we decide to go with the implementation using the left, focus, and the right, so we need to make a constraint that we are working on non-empty list, because it doesn't make any sense to not have focus. Again, this depends on the implementation. You can make your own. So basically, this is the starting point of our zipper. So if we move right, then we are moving our 0, which was earlier at the focus, and we are taking the first one, make it focus. And these operations are constant in time. When we call or move right for the second time, then we are moving the focus to the left. We are taking the first element from the right. As you can see, the lefts are ordered in a reversed way, because adding to the top of the list is cheap. Because we are working with options, then you can easily write the for comprehension or use flat map. So this will be the same. And we can move in the similar manner, go right. So we are moving from one stack to another. We can delete. So as you can see, we delete the focus. And we are always working on the focus. So we delete the number 3, which was our focus. And we took the first element from the right list. It could happen that, for example, there is nothing on the right list. Then this operation will end up with none. Different implementations, for example, can look first on the right, then look on the left, and then return none. So this completely depends on you. We have some method which is called end, which will push all elements to the left, ending with the last element on the focus. And we can have left, and we can move to start. So we will go to our initial object, but without the 3, which we delete at some point. Also, we can write this using the for comprehension, so it looks much nicer. The one downside is that you have to remember that you are working on immutable data. So you have to have this like Z1, Z2, Z3, and so on. So you have to remember not to make a mistake, or you can use something like a state monad, which will take care about this for you. List, the same we can have for a tree. So we can define the tree in this way, that we have an item and a forest, and the forest is a list of a trees. And we can define zipper. It will look a little bit different in this time because we have a current tree and some path. And this path will looks like this, not going into details. This is required to look like this to have this constant time operations. And again, it can have like left, right, up, down, and so on. You can have delete, modify, insert, There are methods like find until or move forward n times and so on and so on. And some final remarks. To make it more safe, you should use state monad. It's also applied to lenses. I know that these were artificial examples. So, for example, I'm using lenses quite often when I have any nested structure and I have to do something with this. I'm using Monocle. And this is a maybe not exact example, but something which I had to do some time ago. So in this example, you have a JSON which contains things like emails and some numbers. And in this case, these are sensitive informations, so we have to make sure that they don't leak somewhere. And for example, if you are doing microservices, then it's very easy that some of the data will be pushed through the API. So you can write really simple lens to replace everything what looks like an email or like a CC number, a credit card number. So in this case, for example, in here, we replace the email with stars or with asterisks, and CC, we left the last 4 digits. And to have this, we need something like this simple optic. Another example when I used lenses was similar. I was reading the configuration, and for debugging purpose, I was printing the configuration on the console. So using the lens, I removed all the passwords and all the sensitive information that they don't leak to logs. Again, this is very easy to obtain to implement with lenses or with optics. The full signature of optics is something like this. So when you are working with lens, you are allowed to change the types. So you don't have, for example, Enigma and car, but you can have Enigma, car, and something. So you can change the input and output types. There are different implementations. Van der Hoven a Profunctor, but this is completely different talk. There are much more optics in the hierarchy. Not even this lists all. And you can implement zippers using traverse and optics, but it's not possible in Scala unless you are using shapeless. Yeah, basically that's all. Thanks. Any questions?